Okay, so nice to meet you all again. Okay, so very soon we'll be meeting up, probably next Wednesday. I think our school already commenced. So this is a rather short lesson. Remember I gave you all homework the other day on the electromagnetic induction and also Faraday law. So this lesson is just a short discussion on one of the selected questions, since one of your, few of you have asked me to discuss particularly this question, although I didn't give the answers for the other question yet, because I want you all to try first. So today's lesson I just discussed this part only, and then probably you'll have one more lesson on video, right, on YouTube. And after which I think the school will already commence, then we can go on a normal basis, right? Unless there's maybe as a request for to do lessons in YouTube for you to review, then maybe I will do it. But other than that, we will continue as per normal in school. Okay, so coming back to our lesson today, if you look at the essay question, paper 3, they give you a dynamo, right? It's a bicycle wheel there. Then they say that as the dynamo rotates fast, okay, the bulb get brighter. This is an experience. Those days, those who are doing cycling with the dynamo. Nowadays we don't have dynamo already in cycle. All are battery operated. Okay, so it doesn't matter, alright. So this is a simple dynamo. It's actually a small generator. Okay, alright. So the theory behind this question is, alright, it's actually dealing with Faraday law. Alright, what the Faraday law says, recapture the size of induced EMF. EMF here, electromotive force or current, you can say, alright, directly proportional at the rate which the conductor cuts through the magnetic field. As you can see here, as the head of the dynamo rotates, okay, this is the magnet connected. So as the magnet rotates faster and faster, as the wheel rotates faster, it cuts the magnet, this coil cuts the magnetic field and the bulb gets brighter. So this is basically Faraday law. But Faraday law is very general. It's very general. So it is just saying that. So what are the factors here? One is the speed. The Faraday, the rate is here is controlled by the speed. Another one is, of course, the strength of magnetic field. Alright, magnetic field. If the magnet is stronger, more field, so the rate of cutting also greater. And number 3, the number of turns. Okay, number of turns of the coil. Okay, if the coil is more turned, also the bulb will get brighter. So in this particular case, is the speed is the one, the factor shown in this particular situation, because we are not changing the magnet, we are not changing the number of turns. Alright. So based on this we have to answer. So the theory, always you must remember, any paper 3 question they ask, usually it's based on some theory, okay, some basic idea, knowledge that you need to know on the concepts they were referring to. Okay, so first what you are going to say, inference. Okay, what inference we make? We can make the inference basically what you observe through the situation given. Alright, so here we can say the brightness of the bulb or the magnitude of induced current. Magnitude of induced, okay, I put short, current, you got right full, induced current depends on the speed at which the magnet cutting the coil. So that's what. Faster it cuts, greater the induced current. Okay. Hypothesis, so it's more specific. Here we already identify magnitude of induced current, speed. So hypothesis basically relate two variables. It's very directly or inversely proportional. Or one increase, the other increase, like that. So we say faster the magnetic field is being cut, greater the magnitude of induced current. Okay, so you can write that down. I'm not going to write, you can write that. Okay. Aim will be what? Aim here will be to show the relationship, again, the same two variable, to show the relationship between the speed at which the magnetic field cut influences the magnitude of induced current. Okay, so you can write that also. You can play my video and then you can write that. Okay, here responding manipulated variable first. Usually we write the manipulated variable, then we look for the responding variable. So here the magnitude variable, the manipulated variable will be speed. Speed of magnetic field speed of magnetic field cut by the conductor or coil, alright, and the one speed, the magnetic field, the coil is cutting the magnetic field, alright. So here manipulator responding. So here we know that Faraday law talking about the rate. So there are three variables I mentioned here: speed, magnetic strength of magnetic field, and number of turns. So once this is manipulated, these two become constant. So the constant will be strength of magnet, okay, strength of magnet or magnetic field. Number two, number of turns. Okay, number one, number two, number of turns of the coil. Alright, number of turns of the coil. Okay, list of apparatus. Now we must have an idea ready. So what we are going to do here, we are going to change the speed of the magnet. Here in this case magnet is rotating, but we also can put the magnet in a vertical way to cut the flux. So the speed, you want to change the speed of the magnet, and then it must cut the coil. So the simplest version of this will be something like this. Alright, the list of apparatus we can write later. I draw the diagram first, then from there we can go back to the list of apparatus. Okay, so here what we do, we set up a paper cylinder. Alright, we put through some coil here, we wind it with some coil. Okay, wind it with some coil. Here we put a galvanometer to measure the current, and then what we can do here, we can place this underneath. Then here we can place a ruler in a retort stand. Okay, this one you can make it a retort stand. Okay, you can hold the retort stand. Okay, so this is a ruler, or meter rule. Okay, this is a retort stand. So what we can do here, we can drop the magnet at one particular height. Okay, so this will be our bar magnet, right? It can be any pole. This is a bar magnet. Okay, so simple. So as you drop the magnet from particular height, the height you can manipulate by measuring with the ruler. So you drop from particular height. So higher you place the magnet, greater the speed. This is from the conservation of energy. Greater the potential energy, it will be converting into the kinetic energy. Alright, gravitational potential energy become kinetic energy. So this kinetic energy, higher the kinetic energy, greater the speed. So greater the cutting of the flux. So as you increase the height, this is the H, then you can control. Here the responding variable, the speed at the, so here the speed is actually, we convert the speed, or we operationally define the speed with the height. Okay, because you know that gravitational potential energy become kinetic energy. Alright, so here the H is proportional to the speed. We can put HV, right? So this is the idea we are using here. So we are operationalizing the speed with the height. So you don't need to count what is the speed using ticker timer, no need. As long as you change the height, the speed is changing. Our concern is to change the speed. You must see there is a change in the speed. So that's what is happening here. Alright? So you already got the idea already. So list of apparatus, you can write the retort stand. And just clearing the video. Okay, so you can note down retort stand, meter rule. Alright, this is a paper cylinder. This is coil, connecting wires, galvanometer. Alright, meter rule. Okay, is there any other apparatus we want to include? So we go back to our checking list, 5 base quantities. Okay, do we measure the length? Yes, so we have the meter rule. Do we measure the mass, the other base quantity? Here is irrelevant. Do we measure temperature? No, it's irrelevant also. Do we measure current? Yes, we measure the current. Do we measure time? No need to measure time. Maybe no need to know the time. It's easy. So the important apparatus here is the meter rule and the others as you see in the diagram. Okay, so we already done that. Now we go to the procedure. So procedure, you just see the idea. No need to memorize. Okay, what you are going to do? I'm going to change the height, and then each time I change the height, I release the magnet. As the magnet pass through the galvanometer, the current is measured by the galvanometer. So we see the reading of the galvanometer. Right here is 0. So we see how far the deflection of the galvanometer takes place. So greater the deflection, greater the magnitude of current. So here we already have the scale. Alright, so that's the basic idea we already have. So now we can write the procedure. Number 1 is per normal we write. Okay, you can write what I'm telling. Set up the apparatus as shown in the diagram. Alright, that's a standard procedure which you won't get marks. Okay, procedure number 2. You have to mention very specifically the first manipulated variable. So you can say raise the magnet for 20 cm from the coil. Okay, raise the magnet 20 cm from the coil. Alright? Okay, number 3. This is the first manipulated variable. Now, how you are measuring the first responding variable. Okay? Raise the magnet, then release the magnet. Release the magnet. Release the magnet and record the maximum reading from the galvanometer as the magnet pass through the coil. Okay, so we already done. So main thing we have done already. You manipulate the variable particular height, then you see what is the maximum deflection. So you already done the 2 important steps here. Alright. So the next is what you just have to repeat only. So you say what? Repeat step 2 and 3. Alright. Your step 4 will be repeat steps 2 and 3 for h is equal to, okay, what is your height? Just now you put 20 cm, right? So you make a reasonable height, right? Maybe 40 cm, 60, 80, okay, 80 cm, and then 100, and maybe 120. So why I am setting here 5 readings? The minimum in SPM we need 5 readings, okay? So 20, 40, 60, 80, 100, 120. We can also make 20, 30, 40, 50, 60. It doesn't matter, right? As long as you have 5 readings here. So, or you want to make it, since the ruler is not giving you 120, you want to make it 60, 80, 3 reading, including 1 for here, right? 90 cm. So it is within the 1 meter rule. So it doesn't matter. If you put 120 cm also, it doesn't matter. So as long as you have your 4 readings, there is 1 reading. So altogether we have 5 manipulated variable, which is good enough to make a graph and to see the relationship between these 2 variables. Okay, so that's the steps. Okay, so you repeat those steps for this. So it's simple only. You change the height. So as you change the height, the speed is increasing. So you see the maximum deflection. The relationship here, as this magnet goes faster, greater magnitude of current, so the brightness of the bulb changes. So you see the relationship. So what the idea of the question is, they want you to catch that if you increase the magnitude of the current by changing the speed, It's related, they don't want to tell you the current, but they say the bulb is brighter. So the brightness of the bulb is actually, they are relating to the magnitude of electromotive force or the current. Okay, so that's the basic idea. So you already done. Okay, so in fact you already finished 90% of the answer. Okay, the next would be, once you finish this, if you follow the order of the question, they want aim, manipulated variables, procedure, the last will be analysis of data. Alright, analysis of data. So here, what is the manipulated variable? What is the responding variable? Right? So you have to put the full data here. Tabulation 1, 2, 3, 4, 5. So here, height, okay, h centimeter. This is actually the speed. Speed. Okay, then reading or magnitude of current. You can say current. Current I/A. So simple. But manipulated variable must be written 20, 40, 60, 80, 90. Here you don't need to write centimeter because you already written here and you must have 5 readings. And then here you don't need to write because you are just telling the examiner how are you analyzing the data. So this one you have to get from the activity that you carry out. Okay, so the last part will be, just excuse me, it's not analysis of data, it's data only. Okay, data, right? Data and result. Okay, data and result. So the next will be analysis of data. Analysis of data. So you just need a graph. So in SPM you just need to write. This is a manipulated variable, h, centimeter. This is magnitude of current. Okay, I versus h. Graph. So that's all. So it's a very simple outline for 12 marks. So this is what exactly you need to do. Okay. So here the manipulator, you can put your speed or you can put your height, doesn't matter. Alright. So this is what actually required for this question. So here you need to have the idea how to relate these variables in an experimental form which you can carry out in the lab. You cannot have a dynamo and turn the dynamo and record the reading of current in the lab, which it can be done, but it's not accepted because the dynamo is already given in the question. So most of the time you cannot use the diagram or the apparatus that is given in the question to put it in your answer. Right? So I think that's all. So with that I conclude for today's lesson. So the next lesson probably I might discuss on the what you call the Planck's law. Alright, so here you please refer to your page 78. So I want you to try this question, alright, the Planck's law idea, and then maybe we'll go through the application of electromagnetic induction in our daily life, and then we maybe discuss a direct current generator, how a small dynamo works, direct current dynamo works. Probably that will be in our next class, maybe it's another short lesson. Then once we meet up in the school, we will continue with the normal lesson as we planned. Alright? So with that I call it a day. So thank you very much, and please go through whatever I've said and answer for the other objective questions and maybe the structural question I'll post to you maybe by today. Right? So thank you very much. So see you in the next class. Okay, thank you very much. Have a nice day.